example, like for the question would be another totally different kind of word or similar simple is really similar to the simple text.
Really similar. Yeah, I cannot say 99% to be the same, right? I don't want to give you percentage, but really similar. Okay, so I can guarantee if you okay, first the ideal way to prepare is first take a look at your homework problem examples, especially for the example I have gone through during the class, and try to work on those sample test problem. Definitely this can be open book, but if you need book to help, that's fine. So if you have no problem to finish those sample problem on your own without looking at the solution, you can just cover the solution, just work on the problem, then check the solution, and you gave right result, or even there's some mismatch, but the result solution makes sense to you, you'll be fine. You'll be totally fine. Okay. I will also provide some equation with the test, which will be useful for your test. But feel free to utilize that 2 paper sheets for your summary. Okay. Let's continue on the line models. On Monday, we mentioned there are 3 types of models, which are mainly categorized based on the length of lines. Because the length of line does matter on how accurately we can utilize which model to study the line. So there are 2 boundary values typically adopted by engineer. So for instance, like 80 kilometer or 50 miles, shorter this lines will be studied as a short line. So for short line, usually you can just take a simple impedance model. And so the capacitance or conductance to the ground can be ignored. So from 80 to 250 kilometers, so from 50 miles to 150 miles, so that is a medium line. So you can take a medium line model. There could be a not unique medium line model, but typically we take a model with a pi structure. But anyway, in such models, we can take the lambda line parameter. The lambda line parameter, which means even the capacitance, resistance, inductance are distributed along the entire line, but we can treat there's an ideal line without resistance, without inductance, but we push all the resistance inductance to just single element. It's just like ideal line, superconductor without inductance, connected in series with a resistor and the inductor. And also there's if we have to model the capacitance or conductance to the ground, they can also be treated as single element. But then the question will be where to place those single elements. But for long line model with lines longer than 250 kilometer or 150 miles, using the lambda line parameter will not be accurate. So in this lecture, we're going to explain why it may be inaccurate. The approach for every line model, as I explained on Monday, will try to develop a transformation of the source voltage, source current as phasors to line current and line voltage as phasors. And there will be only 4 parameters involved in the line. If the line is passive, those 4 parameters can be the 4 entries of a 2x2 matrix. And that 2x2 matrix can be, we can solve inverse, depending on whether you want to transform from the low side to the source side using this transformation, or from the source side to the low side using the inverse transformation. If the line is passive, the determinant of this matrix will be 1. That will be true for all the line model in this lecture, because we don't assume any active source inside of this box. If you do have source on the network, you need to exclude this source outside of network. You only just focus on the lines without any internal source. Then we can calculate the efficiency. For efficiency, we first need to calculate the compressed powers for both sides, and we only pick the active power for the efficiency because we only care about how the real or active power is delivered from one end to the other end, and so the difference will be the loss of the power. And we also treat the source together with the line as some equivalent source. Then we can study the voltage regulation. When the voltage regulation is 0, so this line is perfectly helping the source to deliver the energy. There's no loss. There's no change on the much change on the voltage. So voltage will be perfectly same at the source voltage. Okay, that's what we discussed on Monday, and then we finished the introduction about the first medium line model. We call it the pi model. So this model is widely utilized anywhere in most of the power system. The pi model will take this structure like pi. It just the shape of pi. So it has a series resistance, a series reactance. The resistance will depend on the resistance of line, and the reactance is depend on the inductance of the line. And also we have the shunt admittance to the ground, but because we want to make this model be symmetric for the receiving end and the sending end, so we split the total shunt admittance into half. So totally we have Y. The real part considered conductance, which caused by such as the corona effect of the loss of the energy at the insulator. Usually this part is very small, so most of model just ignore this part, but we do need to model the capacitance to the ground. So we just split that admittance into half. So because we're not sure which side is better to place those admittance, we just split it into half. Then this will be the pi model. And we can derive the transformation, and after some math, and finally we prove the transformation will have this form. So Z here is just the series impedance, which is equal to the resistance plus J times the inductive reactance of the line. So the other three elements are more complex. And usually this atom A is equal to D if this model is symmetric. If this model not symmetric, A is not necessarily equal to D. Okay, and this element C is mainly depend on the admittance to the ground. So if the admittance is not large, and the second element is smaller than 1, so this one is mainly about admittance, but not equal to admittance. If this line is passive, this is passive. There's no internal source, so the determinant of the transformation is still 1. Okay, so that's the pi model. I have to emphasize a number of things just in case you want to do the homework and to avoid some mistake. So when I draw the pi model, I draw Z here. That really means the impedance of the line. And for this shunt branch, I put half Y here. The half Y is equal to admittance, not the impedance. Okay, so which means when you do when you solve any problem, if you see they tell you the half Y here, the half Y really mean the admittance. Admittance is reciprocal of impedance. So if you want to find the impedance of this line, so the impedance is 1 over Y half Y, or 2 divided by Y. So that's really the impedance. So you want to figure out the current. If you know the voltage, you know the voltage added to this shunt branch, you want to know the current. The voltage is divided by the impedance will give you current, right? And voltage multiplied by admittance will give you current. So what I show here doesn't mean the impedance, really mean the admittance. So you see here, right? So the source current, if we apply the Kirchhoff current law here, so this current is the line current. So we want to figure out the current going to the first branch. We use the voltage multiplied by the admittance, not divided by the impedance. So Y, half Y is actually the admittance. So admittance multiplied by the voltage will give you the current. So that's first thing I want to emphasize. A second thing, so this section we only talk about the pi model. But if you have any chance to see other model, for instance, there could be some model, we call it a gamma model. Gamma model, based on this name, you can tell we just push the lambda element to one side of the line. If the line is very short, it doesn't matter which side we place those capacitance, right? We either just split into half for both ends, or we just combine them for one side. The one gamma model even is not very common to use gamma model, but in case you see a gamma model, it can have this shape. We just push capacitance to one side. So this shunt branch total is Y, not half Y, because we just combine the two half Y into a one Y. The impedance is Z, is still same. If this is the case, and you derive the transformation, it's still ABCD, and the ABCD will look like this one. Will not be this one anymore. So ABCD will be, here is one. See, you can try on your own. It's very easy. Just follow the same follow the same way, same method. So A will become 1, D become 1 plus Y times C. So those two are not equal. So which means I try to color them in orange and green, just try to differentiate them into two different things. They are not always same. So only when the model take a symmetric structure, those two elements can be same. Otherwise, it can be different. But advantage of using pi model is you see the total impedance always here and total admittance always there. That's a good thing of using a gamma model. That make a calculation easier. But when you deal with a real system, most model will be pi model, not gamma model. Oh, I just hand out the printouts. Okay, now let's move on. So the medium line model is done, but we'll come back to this pi model because later when we talk about the long line model, we know we cannot just integrate all the capacitance or inductance at a single element as what we did here, or either pi model, gamma model, but we still like this structure because this structure is good with a symmetry of the line, perimeter distribution, and also we can utilize a single matrix to calculate how the load voltage, load source, load current can be transformed into the voltage and current in the source. But definitely, those ABCD will not be just actual, not based on the actual impedance or actual admittance. If we can make any correction, we just manipulate those parameters a little bit, not too much. We can have a model similar to the pi model, but which is also good for the long transmission line. So the line is still passive. So let's talk about the long line model. So for long line model, and we start from the impedance and the admittance per unit length. So we use lowercase, which means this doesn't mean the total impedance, it just means, so this value multiplied by the length of the line, like a 1 mile or 1 kilometer, will give you the impedance of that segment. Similarly, the lowercase y indicate the shunt admittance per unit length. So if you multiply this one by 1 mile, that will tell you the total admittance to the ground for that segment. Okay, we're going to start with lowercase z and lowercase y. And we study very small segment, that x, at the distance. We have to determine the origin. So here, we want to use the receiving end as the origin. So which is distance 0. And so the source of the line, sending end, if the line has a total length of L, so the source end will have the distance L, positive L, and the receiving end will be 0. Okay, then we can have a function. The voltage will be a function of X. So this positive x-axis will go into the lab. That's maybe a little bit different from our convention, but because here we just assume the source on the left, load on the right. So origin will be this receiving end. And if the total length is here, so that will be the source. Okay, we only focus on very small segment of delta S at a distance of X to the receiving end. All right, so because this segment is very small, we can use pi model, right? So it will be fine if this delta, even the total lines can be 250 kilometer, but for this segment, it can be just 1 kilometer. So it will be okay to use pi model. Pi model can be applied to both short line and medium line, as long as the line is not too long. So for this segment, the total impedance will be Z multiplied by the length. And the meters on each side will be Y multiplied by delta S. Okay, so Y is not half because here we treat this model as the gamma model. Even we take pi structure, we just give the right branch to the next segment of delta S. So basically we take a gamma lecture, just make it simple. If you want, you can definitely, we still take pi model, okay? So if we make this one to be half Y, this one to be half Y, this is only for delta S. So if you have a next delta S segment directly connected to this segment, you will have another, right, half Y. They just connected together. So it's just same as this one combined with that one will give you 1Y. So either way, you treat each segment as pi model. On each side you have half Y, but that one is directly connected with another half Y on the next neighboring segment, or you just simply take it a pi model. So you just put like a Y on each side. Okay. Okay, let's continue. All right, so next we utilize the Kirchhoff voltage law and current law to this branch and this branch. So for the series branch, the voltage will change from Vs to Vs plus delta S. So the difference will be the voltage drop only due to this series impedance. So that's delta Sz multiplied by current. Then we also utilize the current. We utilize the Kirchhoff current law. The Kirchhoff current law, this current and that current, the difference will be the current going through this branch. So that current is equal to the admittance multiplied by the voltage. All right. So let's continue, and we divide both sides of each equation by delta X. And we move the voltage. For the first equation, we'll move the voltage to the left, and second equation will move current to the left. So now you see what we're working on right now. We try to develop some differential equation, which will give you more accurate representation of the line. So when the delta is very small, infinite small, so it will become differential equation. So eventually we have two linear differential equations. The first one tell how the voltage can change with current due to the series impedance. The second tell how the current can change with the voltage due to the shunt admittance. Z and Y here are both constant value. We assume the line is evenly distributed regarding the resistance, inductance, and capacitance. So next one, we want to solve the two linear differential equation. We can combine those two into one equation. What we can do is we eliminate the current. Okay, so from the second equation, we can know the y is actually the 1 over y and the di by ds. So we just not this way. So we eliminate the current. So we first solve current, then plug into the other equation. So from the first equation, we can know I is equal to 1 over z multiplied by dv by ds. Then we plug in I into the second equation. We'll be able to eliminate I. So we'll create a second order derivative of voltage, which is back to the distance x. Okay. Then here, there's a parameter which is actually z times y. We call it a gamma square. Why? Because the gamma has some physical meaning we're going to discuss later. But this gave us a second order linear differential equation to describe how the voltage can change along the line. All right, so in order to solve this differential equation, we usually need to have a boundary conditions. So we have the two boundaries. So on the receiving end, so when S equals 0, we know the voltage is equal to VR and current is equal to IR. On the sending end, when the distance is L, so on the sending end, the distance is L. So this is sending end, this is receiving end. We know the voltage is Vs and current is I think it's typo. It's current is Is. Yeah. Okay, move on. Let's try to solve this equation. So here we define the gamma as the gamma square as z times y. So we can define gamma as the square root of the product of z and y. Z is a series impedance, y is shunt admittance per unit length. So Z has a real part, which is the resistance, and the imaginary part, which is equal to omega L. Omega is 377 radian per second for 60 Hertz system. L is the inductance per unit length. Y is equal to G. G is conductance, but usually this one can be ignored. And capacitance multiplied by J omega. So because both Z and Y are complex numbers, so finally the gamma might also be complex number. It will have a real part and imaginary part. We call real part as alpha, imaginary part as beta. So they both have physical meaning. So gamma means propagation constant per unit length. Alpha means attenuation constant. Beta means a phase constant. So we'll explain those constants later, but they all have physical meanings. Usually both alpha and beta are positive. So here you may have questions. So you know how to calculate the square root, for instance, like a 4, right? This one will be 2. You also know how to calculate a negative 4. So this one will be a positive and negative 2j, right? But how do we calculate something like this one, like 4 plus 3j? How do we calculate square root of this one? So we know this one, if we draw the complex number, it will be something like this. We utilize this triangle. This distance is 4. This is 3. So this is real. This is imaginary. So this angle is about 36.9 degrees, right? So this is complex number. So how do we calculate square root? So there are many different ways to define the square root. We can define, if we know the square root, and the square root multiplied by itself will give you this complex number. So one thing you can do is we find a direction which has angle half of this angle. And the lines is only just the square root of, because this distance is 5, right? So for this one, we can assume the absolute value, the length of the the phasor will be square root of 5, and angle will be just 36.9 degree divided by 2. We can define this way. This is simplest way. But definitely, this is easier because the angle is less than 90 degrees for the complex number falling into the first quadrant. But what if we have a positive, negative, real part, imaginary part? How are we going to calculate the square root of a complex number? So we have to assume one definition. We'll take that definition, which is called a principal square root. The principal square root means if you have a complex number, you first change the polar form. So R will be equal to the absolute value, which means R is always positive. And phi, with the angle of this complex number, you only take between pi and the negative pi. All right. So for instance, if you have a complex number, you fall into the second quadrant, okay? So this distance will be R, and this angle will be phi. Okay, you cannot use this angle, the other angle, right? The other angle will be 2 pi minus phi. So if you use R with angle phi, this is actually equal to R with angle 2 pi minus phi. So that means exactly same complex number, but here we take the first one. We make sure the angle is between negative pi and positive pi. Then you'll be able to calculate the square root. The square root basically just you calculate the square root of R, and for the angle you just take half. Okay. Then you will generate the complex number for the square root with the angle less than between only in the first and fourth quadrant, from negative 90 degree to positive 90 degree. So which means, so this angle will change from 90 degree to a positive 90 degree. Okay. So that's our assumption. Then we're ready to calculate things like this one. All right, so if the line is lossless, which means both Z and Y will have 0 real part. So R and G are both 0. So R is removed, G is removed. Okay, and so this J and this J will become -1. And omega will be omega squared. So finally, gamma will become J omega times the square root of the product of L and C. And then we immediately know the attenuation is 0. Attenuation is the parameter indicate how the wave propagating on the line will decay. We'll explain what does that mean. And beta will become pure, will be equal to omega times square root of L and C. We only depend on the indulgence and the capacitance of the line. All right, so let's solve this second order linear differential equation. So for such equation, we can always assume a general solution. Because this equation, a second order differential equation, you solve the equation, it will have 2 eigenvalues. Okay, the second order linear differential equation, if you solve it, you have 2 eigenvalues. One is the eigenvalue basically just a positive and negative gamma, right? So for each eigenvalue, you can have it will represent this exponential function of x. A1, A2 really depend on the boundary conditions. So or where you want to calculate the solution. So we still need to solve A1, A2 using boundary condition. Current will be equal to this equation. So there are coefficient which is square root of y divided by z. We also need to utilize the principal square root to calculate this square root. So because actually we can define, just to make this one easy, we can define lowercase z divided by lowercase y as ZC. ZC, the name is surge impedance. We'll talk about this surge impedance later. This also has physical meaning. So right now you just think we introduce gamma and the ZC, just make the equation simpler. We call it surge impedance because it really means some impedance. The unit will be same as impedance in ohm. Okay, step one, to solve the equation. We utilize the boundary condition at the receiving end when x is equal to 0. So when x is equal to 0, okay, on the equation of voltage, this one will simply become A1 plus A2 because both exponential functions are equal to 1 now. And for the current equation, because there's a negative sign, so will become A1 minus A2 multiplied by the factor. Okay, so because V0 is VR, I0 is IR, so we can immediately solve A1 and A2 by using the voltage and current at the receiving end. So then we'll get the solution by using the boundary condition. So this one will give you the voltage or current everywhere along the line. So you just plug in the distance x to the receiving end, it will give you the voltage everywhere. It will keep changing with x. But those two formulas too complex to memorize. So you see this exponential function of gamma s, and this is another exponential function of negative gamma s. So if you're familiar with hyperbolic function, the hyperbolic function is defined based on one exponential function and another exponential function with the opposite component. So if you have the sum of such function or different such functions, you can introduce the notation, which is a sinh or cosh function. So which will basically just help you to simplify such expression. So when you have exponential function and another one with an opposite exponent, and we calculate the sum, and this one will kind of simplify into I think it's sinh function. The other one, which the difference, it can be simplified by the cosh function. Okay, no, opposite way, sorry. So if you calculate the sum, you have the cosh function, and the difference, you can introduce this sinh function. That one will largely simplify those two equations into those two. Okay, so we're going to utilize those two equations for the following slides to calculate the voltage and current phasors along the line at any distance. All right, so here, x is the distance, right? X is distance to the receiving end. Gamma is a complex number, which is equal to square root of the product of the impedance and admittance of the line. So basically means gamma has, what's the unit of gamma? So Z, the lowercase z had the unit which is like ohm, right? If we use kilometer, it will be ohm per kilometer. And the Y is the meters. The meter is like a reciprocal of ohm or mole, or whatever unit, it's just 1 over ohm. and per kilometer. So Z multiplied by Y will be 1 over kilometer squared. Then square root will be just 1 over kilometer. So which means gamma S, this unit will be what? If X is length, this one has no unit. So this one will be 1 over kilometer times kilometer. So the gamma S has no unit. And ZC, this one, the unit will be ohm. It really means the sum impedance. Okay, let's move on. So we still need to solve the voltage and the current phasors on the sending end. So we'll utilize the other boundary condition when S equals L. So you just plug in anywhere X by L. Okay, so this one will give you the Vs and Is. So I already color those coefficients, so you can easily, by comparing those two equations to the standard transformation, you will immediately know, and A and D will be equal to the cos gamma L. B is equal to the ZC multiplied by the sinh gamma L. And C is 1 over ZC multiplied by the sinh gamma L. Okay, so those will be the A, B, C, D for the matrix. If you try calculating the determinant, which is equal to AD minus BC, so that will become just a cos square minus sinh square. So based on the hyperbolic function identity, so you know this one is exactly 1. So which means the line is still passive. So even we consider distributed parameters, because each small segment we take a pi or gamma model, which guarantee the passivity of the line. So the entire line is still passive. There's no internal source anywhere. Before we move on, we have to quickly introduce some useful formula, because later we'll have to utilize some of the formula to simplify our expression. So far, we have introduced gamma, which is square root of z times y. This one has no unit. Okay, no unit. And we also introduced ZC, which is equal to z divided by y square root. This one has unit ohm. And we also know that the lowercase z is actually the capital Z, which is total impedance divided by the length. Lower y is the capital Y divided by length. Okay, and from the first two formula, you can easily know the lowercase z is also gamma times ZC. The lowercase y is gamma divided by ZC. Okay, next thing we can prove ZC can also be calculated either by the definition or derived from the capital Z, by using this formula. So you can immediately know this one. And from here, we can know that one. So to calculate ZC, the third impedance, you either utilize the lowercase z and lower y, or use capital Z or capital Y, but you need to know gamma. Okay, so with those four formulas there, we'll be ready to introduce the mole equations and to make it simplified. So here, we have accurate model, right, to calculate the source voltage current from the low voltage and low current. And they also satisfy the same transformation we have applied to a short and medium lines. But we haven't have a equivalent circuit for long transmission line. We only have equivalent circuit for a small segment of the line, but we want to have a circuit for the entire line. So how about let's assume we have an equivalent circuit, which has a pi structure like a medium line. But that equivalent circuit is accurate for also this long line. Okay. Because for the medium line, we know the ABCD, will be equal to 1 plus Z times Y divided by 2. B will be the Z prime, and the D will be equal to A, and C will be equal to this item. But here, what we change is we add a prime to each Z and Y. Because the Z prime and Y prime, they do not mean the actual impedance or admittance of line, which just means equivalent impedance and admittance of the line. If we take, we find the equivalent circuit taking this pi structure. So let's figure out what the Z prime and the Y prime is. Since we already know A, B, C, D, right? We just simply let AD, A and D equal 1 plus Z prime, Y prime divided by 2, right? B will be Z prime and C will be this one. So we will be able to solve those three equations for Z prime and Y prime. So first, let's try to solve Z prime and Y prime. If we were able to solve Z prime and Y prime, we'll be able to get an equivalent circuit, which taking the same structure as pi model. And instead of using the actual Z and Y, we'll just use the Z prime and the Y prime value for that equivalent circuit. Then from there, we'll study the long line as a medium line, but we just don't use their actual value. We just use their equivalent value. Does everyone follow here? Okay. Right. So from Z prime is easier, right? From this equation, we immediately know Z prime is simply just ZC multiplied by sinh gamma L. Because ZC is also equal to Z divided by gamma L, so we immediately have this expression. Y prime. If you solve Y prime, you can utilize the first two equations. You plug Z prime into the first equation, and that equation only about Y prime. So you will be able to get the Y prime, half of Y prime will be a cos gamma L minus 1 divided by Z prime. Okay, and because then you already solved the Z prime, you just plug in the Z prime here. You only just replace the denominator part. If you're familiar with hyperbolic functions, you can prove this pink expression is a tangent function. Tangent function of the half gamma L, which is exactly equal to this one. Yeah, that's one of the definition of the tangent function. Okay, if you don't remember the formula, it doesn't matter. It's just one way to make a formula simpler. And you can just go to the Wikipedia or Google to find the accurate formula. Okay, so we'll find the equation to calculate the half of the Y prime. Okay, and we also, similar to the first equation, we want to write this one in the form with the actual half Y multiplied by a factor. Okay, then we can utilize utilize this equation to plug in the ZC. So we'll have this one. Okay, we summarize those two formulas. So capital Z is the actual total impedance of the line. Capital half Y is the half of the total admittance of the line. And the Z prime is the equivalent impedance. So if we can study the long line as a medium line, and half Y prime is equivalent half of the impedance admittance to the ground, if we treat it as medium line. But definitely we know, so if we use the medium line, pi model is not accurate. So we have to make some correction. So this factor is to correct the impedance. And the second factor is to correct the admittance. So adding those two corrections will be able to change the long line to a medium line. Okay, do I have? Yeah, have a. Yeah, let's talk about this one on Friday. All right. So on Friday, I will explain on a real system how the corrected value can be different from the original value.
Nice. Yeah.